Welcome back, everybody. Jay here. Thanks for gathering around Telescope. Feeling a lot better. Getting over this flu bug. Actually feel more like myself today. Uh, I wanted to do a weekly news roundup. I haven't done much of that since this week. So actually, I've been looking at a lot of articles because I haven't been feeling good. I've been reading a lot, and I'm going to share just several, about 4 or 5, with you today that I think are just wonderful. Uh, Come along with the ride. You can read the articles, you can read the summary that I've done, or you can just listen however you want. The first one is called The Hidden Source of Gamma Rays Unleashed by Solar Flares. We're going to dive into the breakthrough in solar physics that finally solves a decade-old mystery about our sun's most powerful explosions and the gamma rays that they unleash. Scientists at the New Jersey Institute of Technology have identified a previously hidden source of intense gamma ray radiation produced during massive solar flares, something researchers have been trying to pinpoint for years. Using data from NASA's Fermi Gamma Ray Space Telescope and the expanded Owens Valley Solar Array, or EOVASA, the team analyzed a powerful X8.2 class flare from September 2017. By combining high-energy gamma ray readings with detailed microwave imaging, they located a specific region on the sun's corona, where particles were accelerated at extraordinary speeds, approaching the speed of light. These particles carry energies in the millions of electron volts, far higher than typical flare particles, and are now thought to produce the gamma rays we've observed through the process called, and I'm going to massacre this like I do a lot of things, Bremsstrahlung, where fast-moving charged particles emit high-energy light when they smash into the sun's atmosphere. The discovery fills a major gap in our understanding of how solar flares work, especially the mechanisms that accelerate particles and generate gamma ray emissions that ripple out across space. It also has implications for improving our space weather models, which can impact everything from satellite safety to power grids on Earth, or even predicting good auroras that are coming. Team isn't done. They're going to keep researching, and the next is to upgrade the EVASOL to EVASOL 15, which will help answer lingering questions from this study, like whether these extreme particles are electrons or their antimatter counterparts, positrons. This could shed even more light on the physics of flares and high-energy particle acceleration. So the next time the sun flares with a violent flare, remember, we're finally closing in on where those most powerful gamma rays come from and what they tell us about our star's hidden workings. You can see I have a link to the article there. You can review it for yourself. The next one, of course, I love supernovas, so you're going to get a flare for supernovas whenever we talk. Next, we're going to talk about this supernova video from NASA's Chandra in decades in the making. This came out yesterday. I thought this was just absolutely fascinating. NASA's Chandra X-ray Observatory has just released the longest ever time-lapse video of a supernova remnant. Sorry, still have the cough, so I have to take a drink. So I pause when I feel something. Anyway, cough coming. So the longest time lapse of any supernova remnant. It's a staggering 25-year span of observations stitched together from data collected from 2000, 2004, 2006, 2014, and 2025. What you get is more than just a pretty animation. It's the dynamic record of this cosmic blast evolution in real time. So let's take a look at it. I'm going to play it really quick. So it's recorded here in the video. There's 2000. There's all the way up to 14. There's 2025, and it will just loop. And you can see it's actually expanding, and they can see that here it's accelerating super fast down here, both in the lower left, lower right, bottom part of that. You'll see they'll go over here to the lower right and talk about how fast this is. And then as you go to the top, they're going to zoom to the top here in just a second. When they go to the top, it's actually expanding up there, the top, a lot slower. Okay, so Anyway, we'll pause that and come down here. I put the link right there to Chandra has a YouTube site, and it has an AI that kind of goes through what's going on here if you want to see that yourself. The star in question was a planet, excuse me, was a white dwarf, exploded back in 1604, and it was a type 1A supernova. A white dwarf, probably drawing mass from a companion star, exceeded the Chandrasekhar limit of 1.44 solar masses and exploded, leaving what's left, known as Kepler's supernova remnant. This supernova remnant, or SNR, now lies about 17,000 light years from Earth. The video blends sharp X-ray data from Chandra with optical imaging to reveal how this glowing shell of debris is still expanding, still interacting with the space around it, and still teaching us about how these stellar explosions shape the universe. What makes this really especially cool is the difference in speed we actually see across the remnant. Some parts are hurtling outwards at nearly 13.8 million miles per hour, about 2% the speed of light. That's what the lower left, lower right was showing you. Okay. While other regions move far more slowly near the top, about 4 million miles per hour near the top of the remnant. Scientists think that that's because the debris on top are plowing through a thicker gas, while on the other side it's a less dense gas, so they're able to expand more rapidly. It's almost like at the top they're hitting a cosmic traffic jam, and on the sides it's just open freeway, expressway, Autobahn. Think that, and they're just going for it. Okay, so it's not just eye candy, it's not just fun to watch. You were watching how the blasted star debris actually evolves, and it gives researchers insight into the environment in which the star exploded, and helps refine our understanding of how supernova seed space with heavy elements that eventually become star planets and even life itself. In this case, probably mainly oxygen, neon, and I'd have to look at the other one, but it's in the article. Anyway, you can go to Chandra's site and see that. So supernovae are more spectacular than fireworks in the sky. They're cosmic engines that drive the chemistry of the universe. The elements forged in these violent deaths are the building blocks of everything around us, from new stars, new solar systems, new planets, life itself, the calcium in our bones, the oxygen we breathe, the iron in our blood. All those heavy elements come from stars that have blown up. Okay. And videos like this let astronomers literally watch how the material spreads, cools, and interacts with the surroundings. And I'm going to touch on that in the Supernova book I'm reading. They really touch on this. Some people will tell you that as these gases go out, they're seeding the environment and forming new stars. Well, actually, when they impact the molecular cloud or gas, as they're spreading, they have to cool before that gas, as the supernova remnant goes out and interacts, it's actually heating up, and the heating up doesn't do much. It's when that molecular gas cools and comes down and forms and condenses. That's where you're going to get stars and solar systems coming from, but those elements are coming from the supernova remnant. So imagine watching a stellar corpse slowly inflate and ripple over the decades. That's the story that Chandra's telling us with this new time lapse. It's a powerful reminder of just how dynamic and ever-changing our universe really is. There's a link to the article there if you want to go see it. Next one. Webb found a platypus. Yes, a platypus out in space. Okay, it's not a real platypus. Let's get into the article. It's one of the weirdest cosmic finds that James Webb Space Telescope has done out of the early universe. And what it is astronomers have combed through Webb's archive of deep field surveys, including data from the Cosmic Evolution Early Release Science Survey, Sears, and pulled out a small sample of tiny distant galaxies that don't behave like anything we'd expect from standard galaxy categories right now. These bizarre objects are incredibly compact. They're very point-like, almost like stars in appearance, even when viewed with one of the most powerful telescopes ever built. But when researchers looked closer through spectral analysis, the light patterns didn't match what we see from stars, quasars, or even more familiar distant galaxies. Rather than the broad, sweeping spectral signatures typical of quasars, which tells us something about the gas that's twirling around at high speeds around supermassive black holes, these platypus-like sources show narrow, sharp emission lines, suggesting the gas isn't moving nearly as fast as in a typical active galaxy nuclei. That's the part that makes them so puzzling and so interesting. Astronomers liken the situation to a real platypus. It looks like one thing, it behaves like another, and it doesn't nearly fit all the boxes we built into cosmic objects. Webb's unmatched sensitivity to both detailed images and spectral fingerprints is what makes this classification possible. What makes the discovery exciting is beyond the catchy nickname. It's that it hints at entirely new kinds of galaxy behavior in the early universe. These objects might represent a previously unknown phase of galactic evolution or a rare relic from the first billion years after the Big Bang. Webb continues to surprise us by extending our cosmic taxonomy, showing that nature doesn't always follow our neat definitions, especially in the distant past when the universe was young and wild. So today we're closing our eyes and listening to the universe whisper back to us, and what it's telling us is expect the unexpected, expect the unknown. With Webb out there gathering data, we're just scratching the surface of the cosmic zoo, and in that image you can see these little star-like galaxies that are small and condensed, and if you actually go to the paper you'll see a graph, and instead of most galaxies having a rounded, these are really steep, showing us that they are abnormal. They're not typical of what we see with galaxies. Thus, they're one thing, another thing, combination of things. They're a platypus. Anyway, hope you like that. Sagittarius A. Let's talk about Sag A, our black hole, and it's been very quiet for a long time. Hasn't done much, okay? But there's hints now of how explosive it's been in the past, and really in the recent past, okay? So, new observations suggest that this usually sleepy monster wasn't always so quiet and may have blasted out X-rays like a cosmic flare gun just a few hundred to 1,000 years ago. So when I say recent, it is recent, just within several hundred years to 1,000 years. Really, that's just like a millisecond or a second in cosmic terms. That's short. Astronomers using the X-RISM X-ray space telescope have captured some of the sharpest ever X-ray data from huge glass clouds near the center of the Milky Way. X-RISM's ability to resolve the energy of the individual X-ray photons with extraordinary precision is like switching from a Polaroid snapshot to a high-definition Technicolor movie. When they dug into this high-definition data, researchers found that the gas clouds glow. This is just random background noise. Okay, it's a light echo. In other words, the cloud is reflecting bursts of X-rays that originally came from Sagittarius A itself, suggesting the black hole flared much more dramatically in the past than it does today, which we suspect it does. This is kind of validating that. Okay. By resolving extremely narrow X-ray emission lines and comparing them to earlier radio measurements, the scientists are able to rule out other explanations like cosmic rays and zero in on the idea that this glow truly comes from a past outburst. Because different clouds sit at different distances from the black hole, astronomers can start to reconstruct a timeline of these ancient flares, almost like reading the geological layers of the Earth, but in time echoes in space. So instead of looking at the soil and being able to read through the geological layers, we're able to see that as time echoes through these gas clouds. This is a huge deal because Sagittarius A is normally one of the least luminous supermassive black holes that we know, barely whispering in X-rays compared to others that roar across the galaxy. Go to M87. Okay? But these reflected X-ray echoes tell a different story, one where our own galactic heart was much more explosive, an energetic place not so long ago in cosmic timescales. Like I was saying, a few hundred to 1,000 years, that's very short cosmic time. Okay? These findings show that even the quietest black holes can have wild pasts. So Sag-A had a big party time in the past. And with instruments like X-Prism, we're finally able to uncover the history in detail. It's a bit like archaeological time travel. Instead of looking at ruins on Earth, we're reading the story of how energy and matter danced around our supermassive black hole long before modern astronomy was ever invented. So next time you hear someone say our galaxy's black hole is calm and sleepy, remember it may have fireworks in its past, and those ancient echoes are still lighting up gas clouds in the galactic center today, which you can see in those images. Okay, last, the road less traveled. Robert Frost. Okay, that's the English dual major for my bachelor's in me. Stars that die off the beaten path in Messier 33. You can see I took this right from the paper itself, and I'll attach it at the bottom as an attachment if you want to read it. This study really focused on looking at red supergiants, Wolf-Rayet stars, and supernova remnants in Messier 33. Basically, in the core, you look at the image down in the lower left, if my mouse has stayed up with me, you can see the part where this image is coming from. So they basically looked at the core region of Messier 33 and were able to plot all this. And anyway, why they did it we'll get into, but it's uncovering a fascinating twist how stars live and die. Not in the crowded heart of star-forming clouds like we often imagine, but off the beaten path. So imagine a galaxy not too unlike our own Messier 33, a swirling spiral of stars, gas, and dust. Now imagine that the giant massive stars in that galaxy end their lives not where they were born, but out in less dense, quieter outskirts of star-forming regions. That's exactly what a new study of the nearby of M33 is revealing. Typically, we think that when a massive star is formed, it basically will live and die pretty close to where it was born, and part of the molecular gas cloud it comes from could still be there. This study is going to show something a little bit different. So astronomers combined data from some of the world's most powerful radio and millimeter wave telescopes, the National Science Foundation's Very Large Array, and the Atacama Large Millimeter Submillimeter Array to map the gas around thousands of evolved massive stars in M33, which you're seeing in that image up here. Okay, we know that the most massive stars end their lives as supernova explosions. These explosions influence how a galaxy grows by their driving winds and stirring gas and seeding the surrounding space and environment with heavy elements. We talked about that in that early article about the white dwarf and Kepler supernova. How much that occurs really depends where the supernova occurs. A supernova that goes off inside a dense cloud of gas will behave differently than one that goes off in a relatively space that's free of gas. Okay, the reality is to study the difference has been very hard because astronomers have a hard time. Supernova are rare events, and they typically are so far away we can't study them in detail. So these astronomers, they reverse that process. Instead of trying to find supernova and study them, they reverse the process by looking at M33 and identifying future locations of supernova. They did this by identifying glass clouds around massive red giant Wolf-Rayet stars and supernova remnants, and especially around those that are expected to go supernova in the future, and mapping those areas. Here's what they found. Conventional wisdom, like I said earlier, suggests that massive stars, the one destined to die in these supernova explosions, should be snug in dense molecular clouds right where they formed. Typically, it's felt that these clouds, these molecular clouds, haven't fully dispersed, and these massive stars die or go supernova pretty close to where they were formed. But when researchers overlaid maps of cold atomic hydrogen, molecular gas, and catalogs of evolved stars like red supergiants and Wolf-Rayet stars, a surprising pattern emerged up there. A large fraction of these stars will soon explode or are located outside of the dense clouds in regions dominated by more diffuse gas. In fact, many massive stars sit in areas where dense molecular hydrogen can't even be detected. That means their supernova blasts won't interact with thick glass like we expected. Instead, they'll send shock waves across less crowded space, stirring up their galactic neighborhoods in new ways. This matters because where a supernova explodes changes how it shapes its galaxy. A blast in the dense heart of the cloud loses energy quickly, while an explosion in a low density region, it will go out farther, it will travel farther. Remember, the heavier the gas, it's going to slow it down, just like with that in Kepler. Remember on the top, they've measured that it was slow because it's hitting a thicker gas cloud. No low density gas cloud, that's like the Audemars. That supernova remnant is just going to go. Okay, and they'll seed space with heavy elements so that they can form new stars or even planets, solar system, things like that. One particularly intriguing example came from a study was a Wolf-Rayet star. It appears to be embedded in a dense cloud until they actually zoomed in with high-resolution data. That's when what they saw was that it was sitting in a 10-year light-year wide cavity, likely carved out by the star's own radiation and winds blowing material off of it. The cavity will strongly influence how the star's eventual supernova interacts with its surroundings. Again, because it's clearing that area out, that 10 light-year area out, that supernova remnant's really going to expand, and probably expand relatively quickly in cosmic terms. By treating evolved massive stars and remnants as signposts of future explosion sites, astronomers can now forecast where supernova will happen, and that opens a new window into understanding how galaxies evolve over cosmic time. So really, what they can do right now is they can only really study this in a computer model. We don't live for millions of years, right? It's going to take for these supernova to go off. So what they can do is say they can take this data and from the study and use it to compare in the computer models and make sure that the models are actually stimulating what's happening in galaxies. And then the model can give a more accurate version or interpretation of how galaxies evolve, and that just increases our own knowledge so we can understand how galaxies develop over time. And so to move forward, research needs to continue. The team plans to expand the survey to dozens more galaxies and produce even sharper gas maps. With telescopes like ALMA, the VLA, James Webb, and future arrays on the horizon, we're on track to map the life, birth, and death of massive stars and learn how they impact galaxy development over millions of years. As they reach out and are able to verify the data they're getting from the first study here in Messier 33, that will just help to refine those computer models, which will help us to refine our own knowledge of how galaxies develop over time. I just find that fascinating. I think that's wonderful. Hope there was something in here that you learned or something that intrigues you and you actually go to the articles and take a look. Thanks for taking the time to listen. Have a great day. If it's clear, make sure you're looking up, and we'll talk to you later.